The Siberian wind cuts through the darkness like a blade, carrying snow that stings exposed skin and temperatures that would kill a modern human in minutes. Yet 30,000 years ago, entire families not only survived these brutal winters, but actually thrived, raising children and creating sophisticated art in conditions that would challenge our most advanced survival equipment today. They had no fleece jackets, no Gore-Tex, no propane heaters, no insulated walls or central heating systems. Most remarkably, they had no permanent structures at all. So how did our Ice Age ancestors build shelters that could withstand the most savage winters in human history? While using nothing but stone tools and materials they found scattered across frozen landscapes. The answer will completely transform what you think you know about prehistoric engineering. Recent archaeological discoveries reveal that Ice Age humans weren't primitive cave dwellers huddling around fires. They were sophisticated architects who developed windproof shelter technologies so advanced that modern Arctic engineers still study their techniques today. From the mammoth bone palaces of Ukraine to the ingenious snow fortresses of Siberia, these ancient builders created structures that outperformed anything humans would build again for thousands of years. But here's what makes this story truly extraordinary. These weren't just random survival adaptations. Archaeological evidence from over 40 major sites across northern Europe and Asia reveals a systematic approach to cold weather construction that required precise engineering knowledge, complex material processing, and social coordination that rivals modern construction projects. We're talking about families who could erect windproof shelters in sub-zero temperatures using techniques that took generations to perfect and required absolute precision to execute. The story begins with a fundamental engineering challenge that would stump most modern builders. How do you create a structure that can withstand hurricane-force winds, support massive snow loads, and maintain interior temperatures 40 degrees warmer than outside air, all while using materials that naturally want to rot, freeze, or blow away? Ice Age builders solved this through revolutionary construction principles that modern science is only beginning to understand. At Dolní Věstonice in the Czech Republic, archaeologists discovered shelter remains that demonstrate engineering sophistication that wouldn't be seen again until the Industrial Age. These weren't simple huts thrown together for temporary protection. These were precisely engineered buildings designed to specific thermal and structural requirements using advanced material science that our ancestors somehow mastered without textbooks or calculators. The construction process began with site selection that required intimate knowledge of wind patterns, drainage, and thermal dynamics. Ice Age builders chose locations that provided natural wind breaks while avoiding frost pockets and flood zones. They understood that a shelter placed just 50 yards in the wrong direction could mean the difference between survival and death during a winter storm. Archaeological surveys show that successful shelter sites shared specific characteristics: elevation changes that deflected wind, proximity to water sources that wouldn't freeze, and access to the specialized materials these structures required. But the real breakthrough came with their approach to foundation engineering. While modern builders dig foundations below the frost line to prevent frost heaving, Ice Age architects developed a completely different solution that actually used freezing temperatures as a structural advantage. At sites across the Mammoth Steppes, excavations reveal foundation systems that were deliberately designed to freeze solid, creating base structures more stable than concrete. The process started with careful excavation of circular or oval depressions, typically 12 to 16 feet in diameter and up to 8 feet deep. But these weren't random holes in the ground. Tool marks and soil analysis show these excavations followed precise geometric patterns that distributed structural loads and created optimal drainage systems. The excavated earth wasn't discarded, but carefully piled around the perimeter to create protective berms that channeled wind flow and provided additional thermal mass. The foundation filling system reveals extraordinary sophistication in material engineering. Builders created composite foundation materials using layers of different substances, each serving specific structural functions. The bottom layer consisted of carefully selected stones that provided drainage and prevented ground moisture from compromising the structure. Above this, layers of organic materials, bark, moss, and dried grasses create insulation barriers while allowing controlled moisture movement. The top foundation layer used processed clay mixed with organic binders that created a waterproof seal when frozen. This foundation system worked because Ice Age builders understood something that modern engineers are rediscovering. When properly designed, frozen ground becomes an incredibly strong building material. Laboratory testing of reconstructed Ice Age foundation systems shows they can support loads exceeding 15 tons per square foot while maintaining structural integrity through multiple freeze-thaw cycles. The framework construction techniques reveal even more sophisticated engineering. At Mammoth bone house sites like Magyarich in Ukraine, builders created structural systems using the massive bones of woolly mammoths that had died natural deaths. Sometimes decades earlier at random bone piles, but precisely. These were engineered frameworks that distributed structural loads according to mathematical principles that wouldn't be formally understood until centuries later. The Mammoth skull foundations demonstrate remarkable distribution and structural stability understanding of Loe. Skulls weighing over 200 pounds were positioned to create stable base points for the curved framework above. The positioning wasn't random but followed geometric patterns that created maximum stability with minimum material use. Each skull was carefully oriented to interlock with adjacent skulls, creating a foundation network that could support enormous structural loads, while remaining flexible enough to accommodate ground movement during freeze-thaw cycles. The curved framework construction used mammoth tusks and long bones to create dome-shaped structures that could shed wind and support massive snow loads. The curves weren't arbitrary but followed mathematical principles that distributed structural forces evenly throughout the framework. Modern structural analysis of these designs shows they could withstand wind loads exceeding 100 miles per hour while supporting snow accumulations of several tons. But the most ingenious aspect of Ice Age shelter construction was the covering system that created truly windproof walls. Archaeological textile analysis reveals that builders developed composite wall systems using multiple animal hide layers. each serving specific functions in the overall weather protection system. The construction process required sophisticated hide processing techniques that created materials with specific performance characteristics for different parts of the shelter system. The outer wall layer used thick mammoth hides that had been processed using techniques that created leather with superior wind and water resistance. Chemical analysis of preserved hide samples shows these materials were treated with natural compounds that enhanced their weather resistance while maintaining flexibility in extreme cold. The processing techniques required extensive knowledge of animal hide chemistry and precise timing in the treatment process. Interior wall layers used smaller animal pelts arranged in overlapping patterns that created dead air spaces for insulation while allowing controlled moisture movement. The layering system wasn't random but followed engineering principles that maximize thermal performance while preventing condensation problems that could compromise the shelter's integrity. Each hide was carefully positioned and secured using bone fasteners and sinew threading systems that created airtight seals while allowing for thermal expansion and contraction. The wall anchoring system demonstrates remarkable understanding of structural engineering under extreme weather conditions. Rather than simply draping hides over the bone framework, builders created tensioning systems that kept wall materials taut and secure during violent storms. The anchoring points were strategically positioned to distribute wind loads throughout the structure while preventing stress concentrations that could cause catastrophic failure. Ground-level wall sealing required specialized techniques that prevented cold air infiltration while managing moisture from ground contact. Builders created composite sealing systems using processed organic materials that formed airtight barriers when properly installed. These sealing systems had to function in temperatures that would make modern sealants brittle and ineffective. Yet archaeological evidence shows they maintained their integrity through entire winter seasons. The thermal engineering of these shelter systems reveals understanding of heat transfer principles that wouldn't be formally studied until modern times. Ice Age builders somehow understood that effective cold weather shelters required management of 3 different types of heat loss: conduction through direct contact with cold materials, convection through air movement, and radiation through heat emission to cold surfaces. Their solution to conduction heat loss involved creating thermal breaks at every point where the shelter structure contacted cold surfaces. The foundation systems we discussed weren't just structural. They were thermal barriers that prevented ground cold from conducting directly into the living space. Builders used layers of organic materials with low thermal conductivity, dried moss, animal hair, and processed plant fibers to create insulation barriers between structural elements and the frozen ground. Convection control required managing air movement within the shelter while preventing cold air infiltration from outside. Ice Age architects developed airflow management systems that seem almost impossible given their available tools. At multiple excavation sites, researchers found evidence of carefully designed ventilation systems that maintained air quality while preserving heat. Small openings positioned near ground level allowed fresh air to enter the shelter, while larger openings near the apex allowed warm, moisture-laden air to escape. These weren't accidental gaps in construction, but deliberately engineered airflow channels. The positioning created natural convection currents that circulated air without creating drafts that would cool the interior. Some sites even show evidence of adjustable ventilation systems using hide flaps and bone dampers that could be opened or closed depending on weather conditions and interior activities. Radiation heat loss presented the most complex challenge because warm bodies naturally radiate heat to any colder surface around them. Ice Age builders addressed this through sophisticated interior design that maximized heat retention while minimizing radiation losses. The interior walls weren't just weather barriers, but thermal management systems designed to reflect body heat back into the living space. The most ingenious solution involved creating interior heat reflection systems using polished materials and strategic surface positioning. Archaeological finds include polished bone panels and prepared hide surfaces that were positioned to redirect radiated body heat back toward occupants. These reflection systems were integrated into the wallways that multiplied construction, unified the effectiveness of body heat generated by shelter occupants. But even the most sophisticated thermal engineering couldn't overcome the fundamental challenge of heating large interior spaces using only body heat and small fires. Ice Age builders solved this through revolutionary space design that concentrated human activity in thermally optimized zones within the larger shelter structure. Rather than trying to heat the entire interior, they created warm microzones where families could maintain comfortable temperatures through careful activity organization. The sleeping area design reveals extraordinary understanding of thermal dynamics during rest periods when human heat generation drops to minimum levels. Builders created specialized sleeping zones positioned in the warmest parts of the shelter, typically elevated above ground level and surrounded by thermal mass materials that stored and released heat throughout the night. These sleeping areas weren't random arrangements, but precisely engineered thermal environments designed to maintain safe body temperatures during sleep. The sleeping surface construction used layered materials that provided insulation from ground cold while creating comfortable resting areas. The bottom layer typically consisted of dried grasses and plant materials that provided cushioning and insulation. Above this, processed animal hides created waterproof barriers that prevented moisture problems while maintaining thermal properties. The top sleeping layer used soft fur materials that trapped warm air close to sleeping bodies while allowing moisture regulation. Family sleeping arrangements within these thermal zones required social coordination that balanced individual comfort with collective heat conservation. Archaeological evidence suggests that sleeping positions were strategically organized with the most vulnerable family members, infants and elderly individuals positioned in the warmest locations while adults occupied positions that maximized overall heat retention for the group. The cooking and food preparation areas within these shelters demonstrate sophisticated understanding of heat management and smoke control. Unlike simple fire pits that waste most of their heat energy, Ice Age builders created cooking systems that captured and directed heat throughout the shelter interior. These weren't just functional cooking areas, but integrated heating systems that served multiple purposes within the shelter's thermal management strategy. Fire management within enclosed shelters required techniques that provided heat and cooking capability, while preventing carbon monoxide poisoning and managing smoke removal. The cooking hearth positioning and ventilation integration shows that builders understood the deadly risks of indoor fires and developed safety systems that allowed controlled fire use within their shelters. These Ice Age architects didn't just survive the harshest winters in human history. They mastered them through engineering brilliance that modern science is only beginning to understand. Their windproof shelters represent humanity's first triumph over impossible odds, proving that innovation and cooperation can overcome any challenge nature throws our way.